brought up about how things consistently get shorter throughout the day because those temperature gradients are more profound, and that's expected to happen. Like, we expect things to get shorter if the temperature gradients that are normally there are there. Okay, and these temperature gradients are consistent. This is why whenever we measure these mountains, like in the papers that I've shared with you guys, like we can actually watch the mountains get shorter every day, and then every night they go back higher because those temperature gradients even out. This is not a conspiracy. This is well documented.
If there's supposed to be less refraction at night, and the less refraction is making them get higher, meaning the more refraction is making the thing sink, that's where we need it to be.
Yeah, the refraction, like temperature, is one of the biggest factors in terrestrial refraction. And it's not necessarily the temperature itself, it's a temperature gradient. And I have many papers showing these temperature gradients along the ground. And then this one paper I had yesterday that I shared actually showed that if you have a temperature gradient of 0.06, then you're going to have like these this droppage. And this gentleman argued that if you have a temperature gradient around 0.06, basically or decreasing as you go higher, then you're going to see somewhere curvature raises to the Earth, from what I recall. Now I do need to look over that paper again, but yeah, he was just saying, like, if you have, and actually other papers were too, if you basically have a temperature gradient that exists, you're going to overthrow that pressure gradient, which they say is going to make things appear higher. It's very easy to overthrow just with a slight temperature gradient. They're totally disregarding this. And those gradients, they're measured to be there every day. Even at night, the ground is still warmer than the air. And so we're going to actually expect that to happen. But then whenever they account for refraction, they say, oh, well, things are supposed to be higher. And then, like, multiple papers I was reading yesterday was talking about how this is BS. Like, they're like, dude, like, why aren't they, like, taking this into consideration? If things are caused, if terrestrial refraction is mainly caused by temperature and those gradients, and then we can measure these gradients steadily here every day, then why are we not assuming that things are going to, be shrinking, assuming that it's going to behave like normal? We should be, but yet for the standard refraction calculations, they assume things get taller.
I wonder if there's any synchronicity to the timing on that optical phenomenon that you're talking about with the mountains getting shorter and taller compared to the tides. I don't know. It just feels like maybe there's some type of connection there, correlation.
Well, it's just optical. But yeah, I don't know.
I'm not saying, like, I know it's not physical, but I'm saying I wonder if the timing when it happens has any correlation to the timing on the tides. That'd be interesting.
Yeah, around 2 to 4 p.m. the mountains are the shortest. Around 3 to 4 a.m. they're the tallest. This was measured like every night in this peer-reviewed paper that was like trying to model out. Basically, the paper, what they were trying to do is make an AI model for refraction where they can basically look at the temperature, look at the pressure and the humidity, etc., and then actually track the mountain peaks. They were tracking the peak of the mountain, and they were trying to like kind of link them up. At the end of the day, pretty much every paper that tries to do this says like it's way more difficult than we can even predict. It's hard to even make, like, they had trouble even making a model for it. Like, I think that at the end of the day, they said that they weren't able to. They could predict it somewhat, but there is always like that variation, just like anomalies, But it's really hard to measure and map and calculate refraction. It's very difficult. And yeah, so they actually watched this consistently happen throughout the day. The mountain would get shorter. That was consistent daily. Every day. No, I don't hear many people actually talking about this, but I mean,
it'd be coincidental not to like call people out or nothing, but I know this is like one of Jesse's big arguments. I wonder if there's a coincidental time on when he made those observations himself, if it was between 2 and 4 p.m.
Well, yeah, and I've told him, I said, look, you need to go do like a 3 a.m. measurement. I tried last week, and I didn't establish my horizontal zero, so I wasn't able to figure out which building was which. So it kind of failed just from my experimental error. Like, I got the vertical level and everything, like measuring the vertical elevation. But you never think to get like a horizontal number 2, just because like we're not measuring that, we're measuring the drop, we're not measuring how much it moves to the left or right. So I didn't get that, and then whenever it came to daytime, I'm like, hey, wait, which building was which? Like, there's a lot of lights across, like, yeah. But I tried to do that, but I have told Jesse he needs to do that at 3 a.m. and he's acknowledged it, but he just says that, the temperature, like, he argues that the temperatures wouldn't be enough to cause the curvature rate. And there are some papers that I was looking at yesterday that argue otherwise. The paper I'm talking about, it was kind of like a little book that I'm talking about, was actually a mathematician advisor to the people who did the Great India Survey. I'm sure you guys have all heard the Glover's reference that survey, because that's what they'll use to say that, we can accurately get things at a long distance because, they were able to accurately measure Mount Everest and stuff from the theodolite. I'm sure y'all have all heard that argument. But yeah, the guy that I'm referencing took part in that India survey. Dude, did Jesse really dip out? Like, what the heck? Where'd he go? Anyway. Telling you, a few of the papers I looked at yesterday are detrimental to people using theodolite to measure curvature. And I have them written down. Like, I have them in my notes on my phone. I have like a spreadsheet per se of like all these different papers, stuff like that. I was actually going really quick last night because I was actually supposed to be doing my own research, but I was like kind of on like a rant, and I was just like on a kick where I just was reading all these refraction papers. But I did get a lot of them down, and once you actually start learning about it and you look up terrestrial refraction and temperature gradients or humidity gradients, for example, you'll see just how profound these things are and how they're not accounting for them at all. And with the fact that these pressure and temperature gradients, these temperature and humidity gradients are there, that's gonna that triumphs anything. That's what they say that you need to mainly measure. But they just focus on pressure. But even slight temperature changes will overthrow their standard refraction calculations for pressure. And one of the papers that I brought up to Ruhif last night, that's what it actually did. It says this calculation's weird. It's not even taking into account temperature. And it was like, look, right here, any temperature difference right here is going to overthrow and cause like significant refraction and overthrow this basic calculation. Which, yeah, they're not like incorporating those that temperature in there. They're just assuming pressure, but that's like very minute. Like, you're going to need to be looking at like temperature and humidity. And definitely consider pressure, but that's assuming all the temperatures are even, which is like almost never the case, except for around 3 a.m. And around 3 a.m., ironically, and other people have pointed this out too in these peer-reviewed scientific research articles I've been reading, that they mention like, okay, they say when 3 a.m. like things are getting taller because it's like higher refraction. But actually, if you look at the temperature gradients at 3 a.m., they're more stable than any other time of the day. Around 3 to 4 a.m. They're like, if you look at the temperature gradient for altitude, it's pretty much a straight line. There's no variation. It's the most even as it will be. However, the very ground, like on the surface of the earth, will be a slightly warmer still, but the gradients like up it. So like I don't remember how high they measure, maybe like a kilometer or 2 or 3. But those were pretty much leveled out completely around 3 a.m. versus if you look at the temperature gradients when they measure during the day, it's like this huge zigzag off to the side, like high temperature near the ground, and then it like zigzags over to the side, and then like basically the temperature then cools off as you get higher, and it's profound, and it's repeatable, and we're not considering it. And temperature gradients that are higher on the ground, higher temperatures on the ground, would cause things to appear shorter. I'm sorry, that's just what it is, and nobody's accounting for that. And they're going to be over here worried about like a plumb bob being a little bit crooked because of mountains gravity. Well, bro, like you're like, what's it called? Like straining gnats and letting camels through. That's a saying I've heard before. Like you're trying to take a speck out of your friend's eye when you have a log of your own. That's like insignificant, you know what I mean? Like, worry about the significant things, And I figured out quickly that it wasn't just me who was actually frustrated about it. these other people who are writing papers on it are also frustrated and very highly confused as to why they're not accounting for these things, because these are the most important things. Crazy, dude. It's almost like they're doing it on purpose. I don't know. It's pretty weird to me and weird to other people. So, yeah. And like, to be fair, they probably only incorporated things like pressure for some of these standard refraction calculations because it is one of the things that would be consistent if the temperature was consistent. Like theoretically, right? You got this higher pressure gradient near the surface of the Earth because of what Ruhif mentioned yesterday, because of gravity. And you're gonna have these higher pressure gradients near the Earth. That makes sense, right? But then, if you look at the ideal gas law, which was referenced in one of these papers about terrestrial refraction, which, by the way, Ruhif said was not applicable, which it actually was in this paper I was reading. If you look at the temperature is gonna quickly overthrow that pressure gradient. Period. But I understand it's like kind of consistent. You can calculate for it, and if that was the case, and if you did have like stable temperatures, then things would appear elevated. But in reality, we don't have stable temperature gradients. We do not, especially not during the daytime. This has been modeled over and over and repeatedly experimented and demonstrated over and over again.
So what you're trying to say is that they used variables that were static in nature to build a caricature of the Earth that they were trying to depict, instead of using the actual variables themselves that would matter.
Well, yeah, like I was just saying, I was trying to give them the benefit of the doubt that, yeah, maybe pressure would be consistent, and in that case, things would appear higher. But it's so minute, like compared to what temperature gradients do.
Yeah,
and
yeah.
like
Pressure is like nothing. Pressure is like a nothing burger compared to actual temperature variation.
Exactly, and this is no secret in these papers. They are clearly stating how much pressure and even humidity plays a huge role. One of the main determining factors in what we see in refraction, terrestrial refraction. But just for the standard calculations that they act like are like legitimate, they're not incorporating for those things, and they're not emphasizing these things whenever people are going out and doing measurements. So it's an issue.
We can always just simplify it. Any deviation from horizontal is always going to be classified as elevation. So what the fuck is curve?
Yeah, but they're trying to use optics to show curvature, and these optics have heavily influencing factors that are not being accounted for. And it's not just my opinion. It's many other scientists' opinion that are researching terrestrial refraction. And it's actually quite baffling. Once you learn about the significance of like how much these variables would actually play a difference, like make a difference. It would make a night and day difference. And they're not being accounted for. They're just like brushing over it, dude. I mean, yeah, there's multiple papers showing mountains swooping up and down all through the night. Now, if refraction was because of a standard pressure gradient and we can calculate for it, then how are mountains shifting up and down every day and night? How are every night they're getting taller and every day they're getting shorter? If it's like if the pressure is like the most important thing, I don't even think that's really
wobblerity of the Earth.
So if that's happening, how can we man, we got to take these things into account, dude.
Was that wobblerity you said?
Yeah.
What is wobblerity? I've never heard of that.
Yeah, it's when the Earth actually it grows and then it shrinks and then grows again while it's spinning, and it goes whoa 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 whoa.
That's funny.